Hello, everybody. Welcome to this session. I'm Mohiuddin Mazumdar from Intel. I co-chair the PCI-SIG electrical work group, and I will be giving this presentation, PCIe 6.0 specification, a high-performance interconnect for storage networking challenges. Let me share my screen. So I will give you a little bit of background on the PCIe technology and how it is evolving. And then I will work and talk about key metrics and the requirements for PCIe 6.0 specification, how we use a holistic approach by optimizing electrical, logical, protocol, and all aspects of this technology to minimize latency for 64 gigatransfer per second PAM4 signaling. I will provide a summary of key electrical improvements in PCIe 6.0 and talk about PCI compliance process, which is a key important aspect of PCI technology, and we'll conclude the presentation. So if we just look at the PCI interconnect for storage, the graph that you are seeing here, it's giving an example snapshot. So if we look at and focus on this blue color here, the bar portion, that is NVMe PCIe based. So as we can see from 2017 and moving into the future, into 2024, it is growing very rapidly. And today, 70 to 80% of data center SSDs use PCIe as the interface because of its high performance, which is exemplified by the data rate and scalable widths available in by 1, by 2, by 4, by 8, by 16. Combination of those two gives the flexibility in terms of bandwidth. Low latency, because PCI directly connects the storage device to the host. It has extended reliability, availability, and serviceability features, RAS features. It is available in many standard form factors, M.2, U.2, add-in card, EDSFF. These are all standardized in the industry. It's also provide low power. And overall, because this technology is used in so many segments of the computing industry, it overall reduces the cost of total ownership by minimizing overall cost because of its widespread application in the industry. Example of usages that benefit most from PCIe NVMe-based SSDs are like database, AI and machine learning, HPC, virtualization, edge computing, automotive, gaming, 3D graphics. Many of these applications just needs basically all of the aspects of PCI technology, mainly low latency, high bandwidth, and faster speed. And all of those features makes this an ideal candidate for this type of solutions. So overall, how the PCI is scaling and maintaining backwards compatibility, this architecture and technology delivers a high performance, low latency interconnect between the storage SSDs and the host CPU switch. What I'm going to give you a little bit of flavor of other usages of PCIe. One of the major driver of the high bandwidth is also the Ethernet network adapters. As demonstrated here on one side, it will be connecting through the Ethernet, and the other side, which is mostly the CAM connector based, is directly communicating with the CPU. To meet a 400 gig Ethernet card in a by 16, you need minimum of 32 gigatransfer per second. That's what PCIe 5.0 is going to deliver. And when Ethernet moves to 800 gig, then 64 gig per second PCI 6.0 will be able to meet. So it is going hand in hand to meet the demands of the bandwidth on the CPU side and on the networking side. Similarly, many applications like AI, machine learning, HPC that we talked about, uses accelerators, and that also often comes in CAM card form factors. And this is a form factor that has been in use since PCIe 1.0, that's spanning almost 2 decades. Similarly, other applications like storage is coming into those factor, and there are essentially you have by 1, by 2, by 4, by 8, by 16, all these form factors to meet the various demands of the bandwidth. Similarly, PCIe comes in form factors like BGA to enable much lower size and compact form factor to mobile usages and other such usages. U.2 provides the hard drives. So all of these form factors will be demanding various types of overall bandwidth. So we expect that as PCIe technology keeps scaling, the many usages will demand various bandwidths, and all of this, the latest and greatest bandwidth and even the lower, will find many usages across all compute continuum. So let's take a look at how PCIe has been progressing as its bandwidth is scaling. PCIe 1.2 started with 2.5 gigatransfer per second with the 8-bit, 10-bit encoding in 2003. And soon it got doubled in terms of data rate with 5.0, keeping the backwards compatibility. As we moved from PCIe 2.2 to 3.0, it was considered extremely risky at that time of the technology, which needs to be low cost, needs to be high volume. And we did not go to twice the bandwidth. We went to 8 gigatransfer per second. But we changed the encoding from 8-bit, 10-bit to 128-bit, 130-bit. And that gave us about 20% improvement into the logic side. So combining the logic and electrical, we got, again, total 2x bandwidth, which is the doubling the bandwidth every generation. Moving from there to PCIe 4.0 up to 6.0, each generation, we doubled the data rate and is still maintaining the overall mechanical backwards compatibility and software backwards compatibility. So industry has been able to leverage and reuse their investment over this 2 decades of time while continuing to the bandwidth doubling for 6 generations. And another aspect is the PCI Express architecture, the PHY standards. What does it provide? It provides a single PHY standard. What it means is that the PHY is the same whether it's a very short channel or a very long channel. So that allows the same circuits to be used across many types of applications, from data center to mobile to embedded. And in each of those cases, it provides a low power, it provides the high performance. Starting with PCIe 5.0, it supports an alternate protocol support. What it means that the PHY doesn't have to use just the PCI protocol. It can negotiate and it can be a bridge for other protocols, which then allows PCI PHY to be used in non-PCI protocols and makes the use of this PHY a much more versatile. So the doubling the bandwidth is happening, as we just saw, for 6th generation now with full backwards compatibility, and it is available in many different standardized form factors. In addition, PCI-SIG provides a mature and a very robust compliance and interoperability program through which industry members basically come together through various compliance workshops to ensure the proper tools are validated, and through that, the designs that are compliant to the spec, can interoperate easily. And this type of program enables an ecosystem maturity in a short period of time. So overall, we see that backwards compatibility with enable broad ecosystem, and it makes PCI architecture a low-cost I/O for diverse applications. Okay. Let's now focus on PCI 6.0. As we are working through this specification development, PCI-SIG expects this specification to be complete by the end of this year. As we started this work probably more than 2.5 years ago, we set some expectations. And the expectation is, as PCI 6.0 doubles the bandwidth, it needs to leverage a lot of the industry ecosystem and installed base and be able to bring this doubling of the bandwidth. So that's the number one requirement, is data rate needs to double to go to 64 gigatransfer per second. We move to PAM4 modulation. This is not new technology, but this is needed, and what is new and what are the specific features in PCIe, we will discuss those in the next few slides. The next biggest and hardest requirement was the latency. PCIe is a load store I/O architecture. It cannot tolerate large latency. So one of the requirements is that even though PAM4 requires forward error correction, which then introduces significant latency, we still cannot allow a hundreds of nanosecond or 100 nanosecond plus latency. Often PAM4 implemented in like networking and other industry standard usages is capable. So we will go through how we address that challenge. Bandwidth inefficiency, because of the additional error correction, all those must be less than 2% error over PCIe across all payload sizes. Reliability in PCIe is not defined by raw bit error rate. Rather, it is defined by a parameter called failure in time, which is expressed in units of errors in billion hours. So this number needs to be much, much less than 1. Channel reach. If we want to keep the data center architecture and platform architecture similar and continue to leverage what we have, then we need to have channel reach similar to PCIe 5.0. As PCIe supports up to 2 retimers, so with the addition of retimers, it allows essentially more than double, the basically 2 retimer. Each retimer will allow full the bandwidth, doubling of the bandwidth. So it provides a huge channel reach, and it has that built into the architecture. Power efficiency needs to be better than PCIe 5.0. And in addition, low power, all the features remain similar to previous generations. Entry and exit latency for L1 low power state, but we also have added a new power state, L0P, which supports scalable power consumption with bandwidth usage without interrupting the traffic. So without introducing much latency, it provides another low power state. Plug and play, it's essentially fully backwards compatible, which means a PCIe 1.0 card can be plugged in a 6.0 system, and then it will work. And similarly, a older system will be able to work with the newer card at whatever the maximum speed both the card and system supports. In addition to all of these key features, it's needless to say that it needs to be HBM ready, needs to be cost effective, and it has to be scalable to hundreds of lanes for particularly server usage in a platform. So we need to make the right trade-offs to meet each of these key metrics. And that's what sort of initiated all of the technical development work and the pathfinding and eventual standards that we are codifying in PCI 6.0. Let's now take a look at what is the basics of PAM4 signaling. This could be just a refresher for many of you. PAM4 signaling is pulse amplitude modulation, where there are 4 voltage levels, as seen in this graph on the right, 0, 1, 2, 3. Now, with 4 voltage level, basically we can encode 2 bits of information. And what that does is, instead of binary signaling that we have used so far, where each of these UI would be representing either state 0 or 1, here we are putting 2 bits, so we can keep the same UI and the same Nyquist frequency as 32 gigatransfer per second. Why is that necessary? At 32 gigatransfer per second in PCIe 5.0, we support pad-to-pad loss of 36 dB at 16 gigahertz. If we try to go to 64 gigatransfer per second NRZ binary signaling, then that loss becomes more than 70 dB for the same channels. And at such a high loss, the receiver noise would be more than the amplitude of the signal arriving to the receiver. So that's a fundamental limit. Without extreme measures, such loss cannot be supported. And that's why we move to PAM4 signaling, as other industry standards for 50 plus gigabit per second have also moved. But what we lose is, now you can see we have 3 eyes. Each of these level from 0 to 1 or 1 to 2 or 2 to 3 now have 1/3 the voltage than a binary signaling would have. So this reduced voltage swing and also the transition between various of those voltage levels degrades both the overall signal fidelity as well as the timing. So even though it solves the fundamental loss barrier, it introduces significant challenges because of this sensitivity to noise. And any noise that could be crosstalk, reflection, or device noise, overcoming those and still provide a reliable signal detection is one of the fundamental challenge. To address some of them, we do mandatory gray coding to minimize errors in UI. We also make pre-coding mandatory to minimize DFE burst errors, which is converted into 2-bit error. So the voltage level, as we have already discussed, at TX and RX defines the encoding. So now in the next few slides, I will focus on how we are going to achieve a solution that is low latency, but is still with PAM4 signaling. As we know, in other standards, PAM4 signaling needs strong FEC, which then comes with latency increase as well as complexity and area and power. So our goal is to address that. So some of the key parameters of interest are FBER, which means first bit error rate, which is the probability of the first bit error occurring at the receiver before any burst error happens. And then error correlation within lane and across lanes is also very important. That's within lane, it could be a DFE burst error. Across lanes could be happening due to common power supply noise and other issues that can give those errors. So BER eventually is going to be depending on the first bit error rate before any burst error is considered, and the error correlation in a lane or across lanes. So how do we handle errors, and then what metrics do we use? So the two mechanisms to correct errors, one is correction through FEC, forward error correction, but challenge is latency and complexity increases exponentially with the number of symbols corrected. So the other mechanism is detection of errors by CRC. Link level retry is a strength of PCIe. It's unique. It has a latency of 100 nanosecond. So we try to combine two things. One is detection is linear. Latency, complexity, and bandwidth overheads are linear. So we make the CRC much more robust. We have a 32-bit CRC in PCIe 5.0, and for 6.0, we make it a 64-bit CRC. And then comes the probability of retry, and the failure in time. That is our metric. So instead of, again, focusing on minimizing per lane effective BER with a very robust and heavy duty FEC, we are looking at the metric of failure in time, which provides us similar reliability as previous gens of PCIe, but relieves us from the requirement of having a very low effective bit error rate and the high FEC latency. So what we try to do is take advantage of the PCIe link level retry mechanism and strong detection through CRC, and then combine those two to implement a low latency light FEC. So it summarizes in this slide that go for a lightweight FEC, use a low latency retry mechanism, apply or achieve a lower probability of retry so that the overall latency remains low. The graphs on the right side, there's a lot of data here, but the main thing I want to point out that this graph here, which on the left side of y-axis is giving probability and BER, on the right side it's giving fit rate. So our goal is again to go to fit rate close to 0 or much less than 1, and the others we are flexible. So the double symbol correct can give us very low effective bit error rate, but it is expensive, as we discussed, and high latency. On the other hand, single symbol correct here, even with retry probability of 10 to the minus 5 and FBER of 10 to the minus 6, we can achieve fit of much less than 1. And we take advantage of retry latency of 100 nanosecond, but instead of going for a 100 nanosecond latency FEC, we make use of link level retry with 100 nanosecond and keeping the probability of that retry very low, and overall giving the failure in time in a range that is compatible with the same reliability that we have always enjoyed with PCIe. Getting into a little bit more details, so FEC needs fixed set of bytes. So because of that, a fleet mode is introduced in PCI 6.0. Fleet stands for flow control unit. So the correction, detection, and retry, all of them are done at the fleet level. So to enable this mode, now lower data rates should also use the same fleet once this mode is enabled. And fleet size is designed to be 256 bytes. Out of that, 236 bytes of TLP, transaction layer packet, 6 bytes of DLP, 8 bytes of CRC, which is 64-bit, and then 6 bytes of FEC. Since now it is a fleet-based, there's no sync header, no framing token, so TLP is now reformatted, and no the transaction or data link layer level CRC. So everything is at a fleet level. So all of those reduction of overhead actually improves the efficiency. So net loss in overall bandwidth is much more reduced. And with this and a single symbol correct FEC and a light FEC and three-way interleaved FEC, we achieved a fleet latency that is in the order of 2 nanosecond for by 16 port and 4 nanosecond for by 8, 8 nanosecond for by 4, and 16 nanosecond for by 2, and 32 nanosecond for by 1. So overall, the key idea is optimize by retry error fleet only with the existing go back and retry. So this is a mechanism PCIe already had, minimizing the retry probability and making use of that link level retry we are enabling. But it provides some challenges on the electrical side. So let me address those. As we have seen, to achieve the fit much less than 1, the first bit error rate FBER needs to be less than 10 to the minus 6. This is almost 2 orders of magnitude better BER it needs to be compared to if we could do a heavyweight and more robust FEC. So this increases the electrical challenges. So we have made a lot of improvements and compromises. The pad-to-pad channel loss in PCIe 5.0 is 36 dB. We estimated that that would be very difficult for achieving 10 to the minus 6 BER. So we go for a pad-to-pad channel loss less than 32 dB at 16 gigahertz. We significantly reduce the channel crosstalk and crosstalk within package and the reflection at various interfaces. We improve significantly the reference clock and CDR. Jitter reduction compared to PCIe 5.0 is about 2x. Similarly, to mimic the receiver improvement, we developed a reference equalization scheme that includes transmitter, second precursor, improved CTLE peaking and bandwidth, and a 16-tap DFE instead of a 3-tap DFE. In addition, we need to minimize the burst error probability. So we mandate PAM4 pre-coding and gray coding, and we also limits the DFE tap coefficients. All of the taps, if, for example, if the first tap is now minimized so that the tap coefficient on the DFE tap 1 relative to the cursor needs to be less than 0.55. So that theoretically limits or lowers the probability of DFE burst error. So this type of electrical constraints will ensure lower probability of correlated errors and hence will allow us to use a very lightweight single symbol correct 3-way interleaved FEC. Going a little bit more details on the electrical side. So a very common topology that we study for PCIe spec development is a so-called one connector CAM topology. What we are showing here is a system host board and a CAM-based card plugged into it. Our goal since PCIe 4.0 has been to allow support of this topology where a CPU or root complex in communicating with a non-root complex, which could be a storage device or could be a graphics or GPU and so on. It has to be able to support at least about 13 inches of PCB routing because sometimes that is the distance physically one has to go to connect and place a CAM card. And that has to be enabled without the use of a retimer. So that's a tough constraint to meet. And what we are showing in this table is the PCI 5.0, that total loss budget is 36 dB. Root complex, which is could be the CPU or a switch, takes about 9 dB in 5.0. And the add-in card, which doesn't include the connector here, is about 9.5 dB. And then connector plus routing, and then the board is 17.5 dB. Since we are losing 4 dB budget from die pad to pad, we tightened the root complex package loss by a dB and add-in card loss by another dB. So that leaves about a 2 dB gap for the system routing. So we can see that by improving the PCB board materials or the stack up, we probably need about 10% improvement in the PCB loss to be able to support similar channel reach as 5.0. But this allowed us to really support very close to PCI 5.0 like channel. And in that way, we would be able to leverage the fundamental infrastructure of the platforms and data centers and still move to doubling the bandwidth in PCI 6.0 time. So let me summarize the key electrical challenges in PCI 6.0. As we mentioned, it's a PAM4 signaling. It requires FEC. We must improve the raw bit error rate or first bit error rate before any correction and before any DFE burst error. And that needs to be at least in the -6, which is very difficult to achieve. Pad-to-pad loss is also reduced by 4 dB to -32 dB at 16 gigahertz. And reference package models improved to mimic the actual implementation, 3 to 6 dB. So it's 1.5 to 2x improvement in reflection and crosstalk. Clock quality has significantly improved. Random jitter is now 100 femtosecond. The TX equalization has been revamped with a second TX precursor, and a new preset table have been defined at 64 gigatransfer per second. We have made TX pre-coding and gray coding mandatory. Improvement in silicon jitter is about 2x. The receiver has been improved with an improved CTLE and 16-tap DFE. Also, we expect even more improvement in the receiver quality by defining a receiver eye mask of the outer eye, top eye, 10% UI and only 6 millivolt, which means a very weak signal have to be detected by the receiver. So it puts stringent constraint on the quality of the receiver that we must have. Overall, by making all these improvements in electrical layer, logical layer, and protocol layer, we are able to achieve a low latency solution. Is still better, power efficiency than PCI 5.0, and supporting PCI 5.0 like channel reach. Of course, channel quality has to improve, material has to improve, and all of those improvements must happen. But we should be able to still bring this PCI 6.0 technology in a fully backwards compatible way in the infrastructure that we have in many applications and many form factors that are going to be in the industry for a long time to come. In the next few slides, I will not probably go through too much details, but we show a glimpse of the type of analysis work that we do to assess that can we reach the channel reach that are similar to PCI 5.0 with all the decisions and requirements we have made in the specification. So we take again a topology which is so-called one connector CAM topology, where a card, PCIe card, is communicating with the root complex. So we make an assumption that the transmitter is the spec-defined transmitter, receiver is the spec-defined receiver, and then pin-to-pin model is where we model the PCB routing on both system and the add-in card. we also represent the package models by the reference package models that are defined in the specification. And then we run the simulation to see whether we are achieving our goal. So this slide shows the eye height versus the system routing length. And the PCB length is from 4 to 14 inches. CTLE index here is shows by exhaustively sweeping the indices that are corresponding to various CTLE cards defined in the specification. And wherever the maximum area is obtained is considered the optimal and achievable. So what this red line shows is the spec limit. For a passing condition, eye height needs to be higher than that. So we can see about 13 inches is where we can achieve some positive solution, which is higher than 6 millivolt. Similarly, while we go higher and higher loss, DFE tap is kept under control to reduce the burst error. So the H1, H0 is the DFE tap coefficient, first one divided by the cursor, is limited to 0.55. So that minimizes the DFE burst error probability. And similarly here, we show the eye width. The top eye width spec limit is 10% UI, and we can again see up to 13 inches, we have more than 10% UI margin. So this kind of demonstrates that with the spec-defined transmitter receiver channel and still keeping the DFE limit to extend to control the DFE burst error, we can achieve 13-inch system routing, 4-inch add-in card routing without a retimer, and hence we can support a wide volume of usages of PCIe intact and bring doubling of the data rate and doubling of the bandwidth. So this would be my basically the last topic or slide. I want to give you a little bit of an idea that how PCI-SIG offers a compliance process. Once the specs are defined, like the basis specification and CAM specification, based on those, we derive a compliance and interoperability test specification that provides all the details of how the test should be done, what are the pass-fail criteria, what equipment to be used, and then what tools to be used. All those collateral then moves on. And then PCI-SIG holds about 4 workshops, compliance workshops, where industry members bring their systems, cards, tools, test and measurement vendors bring their capabilities. And this process continues to develop some mature and robust program for the compliance. And at a certain point, after the specifications are developed, there would be something called integrators list. If certain number of tests are passed at a protocol level, electrical, logical level, then those are considered essentially PCIe interoperable card or systems. And what this process guarantees that if those past systems and cards that passed, if they are put into together, they will work flawlessly. And that's the program provides a path to design compliance. And these are basically what gives a mature ecosystem across many usages of the PCI technology. So to summarize, in PCI 6.0, this architecture can meet the needs of storage interconnect solution in the foreseeable future. We see that this bandwidth provides not only the data rate scaling, this scalable width is another knob it has. It provides everything in a low power, low latency, high volume, and cost-effective way. It doubles the bandwidth with full backwards compatibility. We have seen and reviewed 64-bit CRC, a light FVC, and first bit error rate less than 10⁻⁶, and using link level retry with low retry probability enables a low latency solution and highly reliable with fit much less than one solution. And we are also able to support PCIe 5.0 like channel reach with many improvements in circuits and channels. So I am truly excited. I think the PCIe 6.0 is going to meet not only all the demands that storage will be putting, but also the needs of many other usages and architectures. And because of its widespread use across many segments of the industry, it will be providing a mature ecosystem, very cost-effective solution for all storage, so the demands in the future. Thank you very much. Really appreciate your presence in this presentation and in this session. If you have any questions, please pass those on. I will try to answer them. And again, really appreciate your presence. Hopefully, you got a flavor of what is coming in the PCIe 6.0 technology and in the overall PCIe technology, and you'll consider their usage and effective usage in many applications that you drive and bring to the industry. Thank you so much again.